on this computer. Let's share the screen. Okay. Yeah, just I started working on this one that all of a sudden, okay. So let's go ahead and look at this homework. I think pretty much this one, homework 3, yeah. I think we were talking about this first set. We did this one, and then Y versus X, education. But that's why I was wondering for the second data set, they say to do this pretty much just perform the same analysis test for the fish as in the slid, but substitute weight for the dependent variable. I was trying to do that one, but because I got the fish data, pretty much like the same way we did for the slid data, fish data. Then you don't have to do both of them, just one of them, but just they have like a species, weight, length 1, length 2, length 3, height and width. So then the scatter plot for all the categorical variables, sorry, numerical variable 1, 2, 3, 4, 5, 6. Scatter plot matrix for continuous variable, weight, length 1, length 2, length 3, height and width. So this is okay, but here this next one, number 2, what we have to draw the, so the way that we had the number 2, create 2 groups scatter plot for wages and education. Instead of wages, they tell us to use wages and education. It's very clear, it says, but wages can be replaced by weight, but the education should be replaced by what? That's the one that I was wondering, because by the length 1, length 2, height, weight, they haven't given that one clearly, because these are all the questions for that already prepared by the university. So I don't make it, it's already set up over there, then and then you just have to tell the
Hi, Professor.
Yeah, go ahead.
Okay, since no one's in class, I'm gonna ask a lot of questions.
Yeah, sure. That's good. Take the best use of that one. That's the best opportunity.
So we've done this a couple of times on our homework and in the midterm. So like produce a scatter plot and then describe what you see. What kinds of things are you specifically looking for? Because I feel like my descriptions have been really long, because I'm just like, I'll just say everything I can think of, but I'm not really sure exactly like what
mainly
us to talk
we are
about
looking for this one. Mainly we are looking for that, how strongly they were related. Like let's say for instance that the hair length 1 and length 2, if you're going to put this one, see.
So what we are really looking for is things that are highly correlated.
Pretty much all the, whatever you observe, look at over here. You can say what you can say about this scatter plot, or the overall that whole scatter matrix, because when we're going to talk about the whole scatter matrix, we have to simply go and then just explain that each and every that scatter plots, but these trends are being reproduced on that lower triangle, but these are the same thing. Let's say this one, weight and length. Okay, weight and length, how they are related. Little bit you can describe, but that's why, as you said, that it's, they were expecting the same thing to be explained again and again. It's not necessary, but the thing is that whatever you see, you can just put it over there. Let's say the weight and the length, are they highly correlated?
Okay, so I mean, I just want to make sure that I'm responding with an appropriate amount of information, because, and I should tell you, I don't know if I told you this already. Like I work in data. I'm a data engineer, so I do a lot of this kind of work, but I work on the engineering side where I don't really have to explain what I'm doing. So having to doing the coding is really easy and fun for me, but explaining what's going on is hard because for me it's really intuitive. Like I look at the scatter plot and I'm like, okay, length 1 and length 2 are highly correlated, and you know, like I can see those things without having to like I can understand those things without having to like talk about them in depth. So I kind of don't know like what needs to be said and what doesn't need to be said.
Yeah, but the most of the time, as you said, that is a big question ahead of us, because that what to be said and what not to be said. But mainly, whatever you observe, mainly we are looking into how they have shape. Look at this. Can we fit this into a straight line or not? Mainly.
Okay, cool.
Simple linear regression can be utilized in order to explain the variation of weight by length 1. That's the kind of like thing we looking into. Like here, you feel like, okay, if I'm going to use the simple linear regression without having that linear one, that would be enough for me to explain, because that's the key question ahead of us. You really need to suggest the best model
Got
to
it.
your client.
Okay.
But this one, look at that. Can we explain this one by like a straight line? It's a little bit off, no? Look at this. See? It's going to be fitting into some kind of a what, like a parabolic shape, so that it would be better off that if you're going to go ahead and add another variable to that, this one, instead of length, if you're going to add the length plus length squared, like making like some kind of a parabolic shape, that would make this model very beneficial, because that when you run that one, you can look into R squared. R squared is that key part, which is called the determination coefficient. By looking at this one, we can see that the R squared has gone up or down. So in order to make that R squared like a kind of like a number that which is very close to 100%, would make this particular that model best. But in order to pick that best model, you have to do so many things. That's what we were in that discussion. But by simply looking at this one, you just simply visualize and say, hey, oh, look like this can be explained by a straight line. But that's not even enough for you to make a decision at the end of the day. That's the heavy part in this data analytics and the statistics, because that's why we keep adding all the tests. Next one, what are you gonna do? Okay, you observe this one. Okay, it seems like you have to make like a non-linear regression. Okay, now you're gonna go ahead and add another x squared. Even with that x squared, they say that weight, weight being explained by the x, and when you not the scatter. Let's say that you are planning to do regression here. Okay. Yes, you are exactly right, because you did right, because that it's not about writing the code, it's about how to explain that to the audience at the end of the day, or you get understanding about it. So later on, let's say that this one, see here, instead of like, let's say that you have put the weight here, then you're going to put the length, then you got the R squared, looking into the R squared for that simple linear regression. And later on, instead of that one, you're going to put the weight plus the length 1 plus the length 1 squared. So that will give you like a kind of let's run this one and see. Let's see what's going to happen. Okay, then we have this one scatter plot. Okay. So we have, let's say that data slid, instead of slid, I'm going to get fish. Okay, let's say fish one. Wages, instead of wages, we can go to weight. Instead of education and age, sorry, I'm going to pick one for time being rather than both multiple regression. This one, I would say that instead of wages, we can pick one of this one, length one. One. Okay. I'm not interested in title. So now, okay. Oops. Hold on. this one and see. Okay, then we can see R square is 83%. It's not bad. But since we have a kind of like a fee, look at this one, normality assumption has been satisfied up to certain point. And look at here, see? Data like this looks like that can be easily that fitting into the parabolic shape or polynomial.
So in this case, like a linear regression might not be the best fit, and we
might
should
not be the best. Yeah, let's give a try.
or we should like use another kind of fit model, or we should use we should like make a modification to the
modification and see that what's going to happen. Yeah, that's what I'm trying to do. I'm going to add another x squared term and see how it's going to affect to our r squared. What happened? What? Length 1 times length 2.
You have, oh, never mind.
Squared. Let's see.
Why are we not using the squared function instead of?
Yeah, we can use the squared length. I think it's not the way how it should be. Squared, let me see. What happened? No, the square doesn't. That's the syntax and expecting one of the following name to be this. Why they?
I'll Google also and try to find out how to do.
No, length. Yeah, no. This one should be length times the length. Can you remember we did something like this? Or you have to multiply earlier before we're gonna get in over here. Okay. Length. Okay. See, can you remember?
You have to use star to do square.
We use no already. Use star squared here already. Okay.
No, you have to use star.
Star. Yeah. Okay.
Let's try that. That's what the first thing on Google is telling me.
Why? Yeah. Should work now. Yeah. Yeah.
No.
Yeah, because this has to be done because they think this is no. I know the problem. I think this is the problem. Sometimes because they're gonna take because this. Let me see. We had something like that earlier. No, you see, you have to multiply earlier. Can you remember we used to do in chapter? We'll go back to see. Can you remember? No, not this one. Not chapter 5. Homework 2. Not the homework. Chapter 5. Can you remember we did the 1 over inverse one? We had to make it ahead of the time. So I'm going to show you that one. Media. There's bonus. Here be chapter 4. Chapter 5 actually we had that one. Those kind of yeah, there you go. See, you're gonna make it earlier. I'm sorry. Here, see, inverse we're gonna make earlier and then fitting into this one. But this one it work over there. Let me see that why it did work. See, can you remember month? See, month did work. See, month squared. See, look at that. Because the problem is you cannot do that one with the reg. You have to go to GLM. That's the problem. See. Homework 3. See, that's why they say that reg does not work that one. Then you have to go to GLM, generalized linear model. Reg and GLM both you can utilize. So this one, just say data out fish. Fish, okay, we don't need this one. Okay, model would be weight. That's the benefit of using this one. But if you want, you can set it up earlier too. So this one, length 1, as you said, let's put the length length squared.
Oh, is it because there's a 1 at the end that it was computing 1 times 1?
Yeah.
Oh my God, SAS is so dumb. I hate SAS.
So let's run, as you said, that like this one with the GLM. Generalized linear model. That should work. Oh, why it's not okay? Then if that's the case, to the square month, oh, sorry, not the month. Oops, no, length 1. I'm sorry, length 1. Length 1 square. Why it's not given? Length 1, no, just length. So the weight length 1 times length 1. This one should work. Yeah, they don't take that to square because of the numeric. That's the problem. Yeah, should be in
That's
this
so
one.
silly.
Yeah, see?
So silly.
Yeah, it has to be in this one because the program doesn't say it like that. So you cannot use the reg. Reg doesn't work with just one. You have to use this one. Or you can see, look at R squared. Let's go ahead and look at the R squared. Where's R squared? See, R squared 84 now. But earlier it wasn't bad earlier. I mean, like earlier you had what did you had earlier? This one. Not this one. I'm not talking that one. The two. I'm talking about not this one. One that had earlier. Okay, this one. Length only. You can for that linear one. You can run either one with the reg or this one. Okay, they both if you run together. Can compare contrast and see that they are square mainly. This one for the second one, the weight, and you have a length 1 and length 1 squared, so that should be R squared 84. But if you have a standalone R squared only, see, length 1 only, I'm sorry, length 1 only, see, 83. It has a little bit improved, just a little bit. You can even see that in this particular the graph, it's not a big deal. See the weight, that's not a predictor value. I mean, like here, see, it's not that bad. See, everything being captured by this confidence band. See, that's how they say this kind of like this band and prediction band. See, so pretty much everything being inside. That means like we saw that confidence interval. When you're gonna looking into the confidence interval for a given this value, the confidence interval is given by this point and then add something to this side and this side. They go like a band, like a band. See? So that's the one that we had over here in this slide. I'm going to show you that. Especially this one will very important. So if I'm going to go ahead and look at the confidence interval band, okay, I'll explain you what that means. So week 1, week 2, week 3, we mainly have chapter 4. Let me see. That's the place that you have. Let's see, multiple, not the multiple regression. You don't need the multiple regression to get this done, but without regular one, I'm gonna get the simple linear regression. We have that one in week 1, chapter 1, chapter 2, chapter 3, chapter 4. Okay. So this one, okay. See, analysis, interaction, regression analysis. This one data, we'll talk about this, not necessary. Then just go to the next one and have a look at it. 2, let's see what they have. Sampling, descriptive statistics, they were not talking even about that. Regression comes into the picture in chapter 3. Okay. Okay, this one. So this one, basically, we were talking about the regression line, how that can be fitted, data can be fitted into a certain model, and how the error can be calculated. And the B1 and see, B1 and B note. We don't do this one by hand. They're going to take into account all the XY terms and then sum them up, this product. Between each and every data points, X and Y, you're going to multiply together, see, like this. These two together, that's called this one, and then sum them up. And X squared, and the Y terms, X terms, and then plug in into this one. So the summation XY is nothing but summation XY is 196. You're going to multiply X and Y. 1 times 3, 3, 2 times 2, 4, 3 times 8, 24, 4 times 8, 32, 5 times 11, 55, 6 times 13, 78, like that. And later on, we're going to sum them, see, okay, across the rows. See? So, like, that would be this, and this would be what? Summation of X terms only, see, summation of X terms only 21. In this term would be summation of Y, which is 45, and divided by summation of X squared. Okay? To get the X, you're gonna square, 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 and then add them up, which is 91. That part is 91. This part is again summation X, which is 45 square. That's the one that they plug in into this formula and calculate to. And later on, you need the Y bar. Y bar you can easily calculate by, you get the Y divided by number of observation, 1, 2, 3, 4, 5, 6, 45 by T by 6, which is Y bar. And B1 already calculated, and X bar would be summation of 21 divided by 6. So that's the one they plug in into this one and got the 0.2 and 2.2. We don't do by hand. People used to do by hand. See, those things we learn over there. Then we fit in into our model based on those two, that heavy two formulas. Okay, then fitting into that one. And mainly when we talk about that counterpart of the population part, see, in a population, it behaves like this, not like a scatter plot. They behave like given for 12. Look at in that sample for a number of ports. If it is 12, you have one data point. One data point for 12. This is a sample version. This is what we're gonna do with the aid of with the aid of the given data. This is what we are working on. But how did you know that this should be calculated like that way, and how do you know that it should be fitted into that? Because we believe that it's been like this way. For a given, you don't have only one data point. They believe they have infinitely many data points which can be modeled with the histogram and a distribution like this, and it is having its center here. So does it this one. We are drawing only for 3 of them, but each and every that node, the way that we have here. See, I'm sorry, not this one. The nodes one. Yeah, number of ports. No, is that the one same thing? The cost versus here, number of ports here. Around the regression line, see, nodes. See? 12, 30, 68, like that. See, and this is the population version. You don't have a B. You have a B node. You have beta node and beta 1. That's the one that we're gonna estimate. On the other hand, then when you estimate this one, we call that one beta node, we call the B node. Beta 1, we call the B1. So with the aid of that population model, see, we're gonna just build up the sample version. So later on, you calculate, see, this unknown quantity that needs to be estimated from data. That's the sum of squared error, mean squared error, which is called the squared residue, see, which is the estimate of the population. Error is distributed according to a normal distribution. This is the error variance. It's nothing but the error variance. Error variance. You have to keep in head that it is the error variance, not the variance of the given data. I'm not talking about, let's say, this data set, not the variance of this guy, neither this guy. No, I don't need the variance of this guy. I don't need the variance of this guy. I need the error. How do you get the error? You have a y variable for given x, y, and then later on you're going to fit in into this one and calculate your y hat. See, y hat. For a given x, you're going to calculate y hat. For, let's say, for instance, for a given x equals 1, if you want to calculate y hat, see, you're going to plug in into equal 1 over here. Then you're going to get negative 0.2 plus 2.2. Then 2.2 minus this one become 2. Okay, let's say 2 is the same value. No, y was 1, 3 over here. Your estimated value is 2. Their gap is how much? 3 minus 2, y minus y hat. Y minus, you can include another column over here, another one. That column would be y hat. So this y hat would be 2. And then you can get the error, EI. That column say that, let's say the error. So error should be 3 minus the value over here, 2, which is 1. Okay. Those error terms, we are really interested in error terms. Error terms they are like a data set. That error has a standard deviation. Error has a variance. That's the one we are really interested. That one you can easily get by the mean squared error, which come along with the ANOVA table. Look at here, this ANOVA table, this guy. Oh, it's already clearly mentioned here. This is nothing but root mean squared error means mean squared error square root, which is the standard deviation of the error. Standard deviation, estimate of the standard deviation of the error, not the y, neither y nor x, error. This is the standard variance of the error. It's the variance of the error. See, this is what? This is the sum of squared of the variation. See, error variation, how much error being varied has been divided by this one. That means average. In another way, we call that a mean means average. See, how do you get that one? Always average by dividing by degrees of freedom. That's why when we need the sample mean, we're going to divide by n. N would be my degrees of freedom. So you're going to get that one. See, those things they were talking about here. So error, see, very interesting. See, that's the error variance. Error means error. So later on, what they did was see, for a given B1, they created a scan. There's some kind of a confidence interval. This is not what you're gonna see here. This is different. This is for a given x value. What would be that weight regression? Okay, that one come from this one. See? Okay, this one. Keep going. Not this one. Let's go to the next one. Second slide. This one, part 2. Here. See, keep going. Google the ANOVA table. We're talking about the ANOVA table. This one. See, and we are here. Okay. Now we are here. See, for a given, see, we are really interested in the average, expected value of the average. That's what we are looking for. Instead of that one, they're going to go ahead and look from the confidence region. Okay, confidence region is nothing but, they don't say clearly, but they have given the 2 parts here very clearly. Okay, this is nothing but, sorry, not here. Okay, that's the standard error. Okay, that means, see, that's the one. That one of them, see, for estimating the conditional mean of y that occurs at xn, at x, for a given x, what would be the length of this, not the point on this one. It's not enough. You get that guy, and then you're going to subtract and add this length, this much for the standard error. This whole thing, sorry, margin of error. This is called the standard error of that value. The standard deviation of this curve. or individual that one, or mean value. See, mean of that one or individual of that one. There are two things we can look into. If you looking into the mean, see, estimating of the mean at that point is, this is the mean at that point is XM. M stand for the mean of the mean. So the standard deviation of the mean. Standard deviation of the, if you have individuals, see, if you examine the formula, you can see that the second term will be 0 if this one. Okay. So standard error of the mean. I need the standard error of the, say, suppose we are interested in predicting the cost of a new communication node that had 40 ports. You really need the predicting just the simply the cost, not the average cost. Average, not the average cost, that's the cost. How do you do that? See, what's the quantity we are estimating is this one. But here we are doing the mean. That's not what we're looking into. We are looking into two things, I think. Let me see. SM, they have this one, 1 over n. This part xm minus x bar. Okay, we saw that one. That's the individual one, not this one. There you go. See, now individual one, they have added another term here. See, so prediction standard error, prediction of standard. That's the prediction confidence interval. So those are called the predictions. These are called the confidence interval. So there are two lines going over here. So that there are prediction one and confidence one. So that means confidence interval means that you are looking for average. See, average, this guy. Average of estimate. So, this guy. Not only like that, but you need as a like a range. See, that's the one. This is called the interval estimate. See, interval estimate, confidence interval for the mean value of this one. That's the bar we can see over here. It's small bar. That's for the mean value. But instead of that one, they were thinking about you have to prediction for the predict. Instead of x1, you can predict the weight. In this case, for a given length one, you can predict the weight. Or for a given length one, you can predict the expected weight. Sorry, the average weight. You can estimate the average weight for given each and every length. Those are going this way. So you are adding confidence interval this way. Okay. So one for prediction, one for the other one. So that means it's on a little bit clearly. If I write over here, you can see very clearly. So that's the same thing. They were expanding all the way to the up, all the way to up. See? So while I'm gonna get this connect all the way up to that one is called the prediction. The other one is called the that graph very important. What you see over there. So this one interval, we go one more time. This one would be given by see confidence interval. This one prediction interval. This one, see, look at for the same thing. See, confidence interval should be for the same number of would be this to that. Prediction interval should be 32, 872 to 52. See, it's large. Prediction interval is large all the time. See, these are prediction. That's why they say the dotted line. Say prediction, thick line, this one. But that can be done for each and every given x. See? So they say they compute. See, computed this to that. Then what would be this one? It does not list SP. See, that means. See? So this should be prediction standard deviation. So this is how they have calculated this one. I'll give a rough idea. You don't need heavy. See this part. See. This means like this. This is what they were talking about. let's say that you have, if you have this length, okay, so this length, so we have this scatter plot, our scatter plot, okay, like this one, right? Yeah, it's coming up. This scatter plot, see, this one is the weight, this one is the length one. So you have a scatter plot like this. It's scattered over this and the baseline. You get the baseline. You know how to write the baseline equation of this one. This one is nothing but y hat equals b naught plus b1x. That means weight estimate b naught. B naught is already over here. See? B naught is already over here. See, negative 462. Right, first one, then show it 462, 22 or 23 plus 32.83 times length 1. That's the equation of that one. So every time if you have a length, if you plug in into this one, you can easily get the estimate. They say that means they go over here for a given any x. Any x. Let's say I'm gonna call that one xm. See, for a given x, any x, you need this one, you can get that one. See that point. This is nothing but y hat m. How do you get that one? That means weight for given length m. This one. See, you can say weight. See, hat is nothing but y hat m is negative 462.23 plus 32.83 times, see, xm. Let's say 5, you're going to plug in into 5 and find that one. They say I'm not interested in that one. They say give me the two bounds up and see this one and this one. These two, see that one. That's called the confidence interval. So why confidence interval? The interval, confidence interval. I'm going to say CI, confidence interval. How do you get that one? That's the one they were explaining over here. How do you get that one? See, the quantity we have, you have already calculated. You go to something called the SM. You calculate this guy. You need the XM. You need the X bar. You need the number of pairs. You need that standard deviation of X. See, and you need this guy. We have this guy. This is nothing but the mean squared error. This is nothing but given. This is you know how to calculate. You know how to calculate. You know how to plug in all these, and you can get this. So that's why they say that if you need that one, confidence interval 4, which guy? Expected value of. If you're interested in expected value of, see, confidence interval for the expected weight, per given length, xm, confidence interval. This is the just the weight. See, this is the estimated, see, estimated weight for the given length 1 xm, given length 1 plus xm equals xm. So how do you write that one? They say it can be written same thing you have over here, y hat m plus or minus standard error, plus or minus standard error, plus or minus standard error. So see, so this standard error is the one they have given like this way, y bar hat plus or minus. Standard error is the one they have given like this. Like that. this heavy formula. SM has been given by y hat n plus or minus SE square root 1 over n plus xm minus x bar squared over n minus 1 sx squared. I wrote that one here so you can see. Okay. So you know xm, you know x bar. See, they calculate for us only for this confidence. Similar fashion, you have a confidence interval like this for each and every xm. Okay. Okay. Like that. So that's like a band now. See, band. That's what we call the confidence band. Confidence band. In a similar fashion, you can write the prediction interval, PI's prediction interval, okay, for the expected, okay? For the expected weight per given length one equals at the, let's say xm, okay, say that's the same thing they were talking about. Okay. Now this time they're gonna add the same, you done that one. Now they go to the prediction. See, predicting interval for y given a. Actually, not the expected one. That should be prediction interval for the not the expected one. Prediction interval for the single one. Weight per given length. It's being given by again y hat m plus or minus standard error of, they call the p. That means they have make a small here you have to multiply this by t2, okay, t value as well. So you have a t value plus the same thing but with a small adjustment. That's it, and it's been expanded now. See, they added one. That's it. They added one to the formula that we had earlier. 1 plus 1 over n plus xm minus x bar. Or if you want, you can say for the prediction yp minus x bar squared n minus 1 sx squared. That's the one gonna come over here above that one. See? Those are the prediction bands. See, those called the prediction band. It's bigger than the other one for each and every data point. So but the formula would be the one that we had on this one. We don't use the formula and plug in that one and looking into one by one. You cannot calculate for each and every data point. It's very rigorous. See? You go to the next data point, next one, because they are continuous. For a given any length, you can give the estimate, you can give the point, you can give the interval, you can give the whole thing. See? You can predict something, you can give the confidence of that one rather than give the point estimate, interval estimate, prediction. If they ask, okay, how do you predict that? What would be the weight? It's going to be in which range that you can predict that one. The prediction interval would be from here to here for given xm. How would be the estimate? Estimate would be this one. Instead of giving that one, I would give you a range. That range would be from here to here. So for a given any problem here, this one is playing a heavy role because the prediction and see this small thing here very clear. See, for they say that given 50, you go to 50. This is the estimate, point estimate. What would be the weight? Estimated weight would be something you can say around 1000. Okay. Now we say no, I'm going to give you an interval 1000 minus standard deviation, that standard error, 1000 minus plus standard error. That would be as a range. Or I need the prediction. How could you going to predict that what's going to happen to weight for future? If somebody going to come over here like with this one, with the length, if you're going to catch like any fish, let's say the fish with the length 1, what would be its weight? You can predict. You can predict. Prediction is not the confidence interval. Prediction is the prediction interval. You give the prediction interval. and anything right beyond. Okay, that's the one that we really wanna explain. But as you asked that, I mean, like by looking at this scatter plot, what we can get, those are the things that what we did was that we had the length, we square that one, we saw that it has been improved that just a little bit. So that means this is enough because it's going to be between the prediction interval, and then it's kind of like a capture pretty much everything within that range. So see, all the data points are over there. So that's why that when we train this one for the fish data scatter plot, like that. So here, but very different way that what kind of adjustment we can do in order to make this one that really that non-linear. This looks like a big cluster. You can expand the cluster by taking the log on this side. Different recommendation. You take the log and take the log on this side too. And we did that kind of a transformation for in order to make this one more that more linear. Once you become linear, once you get the log on both sides on the length 2 as well as the height, so that can be easily fitting into some kind of a linear regression model. So those kind of a thing we were expecting that you to explain at this stage. And then on the other hand, that instead of that one, it does in a simple linear regression. But what we're gonna do normally, instead of throwing this one, you plan to throw another variable to here to explain the weight at the same time. The same way in this case, instead of that just explained by one variable, we were planning to throw to explain the wages. I throw that education and age both in the beginning, education and age only. See? Education and age only. Even before that one, if you want, you can put the education and see what's going to happen. Let's say education. See? You're going to throw like one variable. Let's say that you're going to throw only education. So data slate, education only. The regression on using education, not the age. Variable as regress to predict wages. So in this case, if you run regression, you can see R squared, see 0.09, 9%. 9%. See, look at the one residual quantile. You see, doesn't fit in into this one. Looks like this normality assumption has not been satisfied. See, serious issue. Look at here. The bands very big. They have to be very thin all the time. See, the prediction bands are. See, look at what happened. They were even all the data being even outside the bands. Prediction band. See, this is a confidence band. Prediction band. So your prediction is very, 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 very lengthy. That means that doesn't make any sense because you cannot explain something with like a large range of values. You can predict large range of values. If that's the case, there's no point of using statistics and data analysis. On the other hand, look at this one. It seems like it's not going to residual. That quantile plot not going to fit in into the way that we really need. It looks like it's a skewed. Whether it's going to be right skewed or it looks like this one left skewed. See, this one is up and going like to down. So this, see, look at this one, funnel type. Residual was the predicted value. Funnel type. The assumption of this one, the same variances for all the regression. That all the normal curves for the same variances, that assumptions will be violated. So nothing is good. So those things are the one that see assumptions are not satisfied. If that's the case, what are the remedies? You feel like, okay, with the education, we cannot explain the salary. Wages cannot be explained through the salary because the education is just like one of the key factors to explain the wages, but it's not the case all the time. See, most of the time, experience, so many things. See, the age, they added now age, and see now what's going to happen. if you had another variable? Would that both variables are important in explaining the wages? Let's see. See, now it has gone up at least, see, 24%, see. By adding another variable, it has gone up, something useful variable, see. 24, see. They're still the same. If you look at the still the that funnel type. And we don't even have a that because it's a multiple one. We cannot come to that same formula. So okay, it's a different way we have to handle. We don't use, but now it's become multiple. The multiple regression, you don't talk about those things that we talk about the prediction interval, but those are not here displayed because those are handled by the matrices. So simply you can talk about that R square. So later on they added another two variables, gender and language. See, by the change in this one to some kind of a numeric values, we had that the strings. Okay, we're gonna run this one. And let's run the regression and see that when we have four variables to explain that doesn't matter categorical or numeric, how could that wages, which is a quantitative or numeric variable, can be explained by those variables? And those variables would contribute positive to explain the variation. See, not that much, 29%, but doesn't matter. See. So what are the other variables you can think of adding to this one? Sometimes we don't have other variables. That's why we're going to go ahead and take the log wages, because the way that it has been scattered. Remember, log wages being explained by those four variables and see there's any improvement. This is 29%. Now you're going to take the log transformation on this one. See, let's keep a little bit up now, 30%. We like that. So in addition to that one that you were thinking about explaining this one with the aid of that just the levels of that one with the dummy variable. One dummy variable is enough for you to explain that the gender, and two dummy variables are enough for you to explain the language. That's what we were doing over here. And with the aid of that one, if you do that one with this many variables, you can look into R square too. Let's see what's going to happen. See? It's not going to change because that's the same thing that we did earlier. But when it comes to the explain something and say that what would be that salary, estimated salary for the person who has the knowledge in French, okay? We can say that what is the salary of the person that who has an education, such education, certain age, and then the man or woman with a certain language skills. And on the other hand, we can check and see whether English and French gonna contribute to this one. See, look like they don't contribute. See, you can reject them too. See, you can reject them too. See, sorry, reject them. So we do not reject. We do not reject the null hypothesis, which says French cannot contribute, in English is not contributing. Those two we do not reject because of the your higher p values. So you don't reject. These are not contributing, but the gender contributing, the age contributing, things like that. Those things you can observe. So that with that said, I mean, like later on, what we did was that yesterday we had that discussion that we pretty much were planning to go into the most that we were talking about that best models. So in this best model, what happened was that we were, when the certain number of variables are given, we were trying to get the best model through certain criteria. That's why they say here, if an import, see, previously we discussed the sum test, t-test and partial test, and the overall test to help us to determine with a certain variable, especially overall variable too. Overall, partial, t-test help us to check and see which variables to be included in the regression and which one to be taken out, even though they still in the, let's say that they were in the regression, but it doesn't show that much of improvement for the model. And then what are you going to do? You're going to add one at a time and see what's going to happen. That's the kind of a thing we are looking into trade form. You get the education. Later on top of education, you're going to add the age. On top of that one, you're going to add the gender, language, and those kind of a thing. And before you're going to get into that one beforehand, to make us that kind of a procedure, apply that kind of procedure, we apply these ones too. So you have a t-test and see which one to be included and excluded. Partial test, you can see which one to be included or excluded. F-test, if they were not, see, if an important variable is omitted, as I mentioned yesterday, by any chance, because of this setup, by accident, with the aid of this one, you don't know. By looking at the number, you have omitted one of the best variables. Because that's why that has been prevented. That will be checked by going through this kind of a method. That's why we are using different kind of a strategy, and then we're going to systematically using a certain algorithm to come up with the best model. That's called the backward elimination, forward selection, and stepwise regression. So in addition to that one, see, since they were not guaranteed, you get the right model, because now we'll see this issue. These three methods are not talking about the residuals. See? They do not check the residual assumptions. See, or search for omitted factors like curvature. They don't even look into that omitted factors. And none have the ability to use the researcher's knowledge. So when you use this method, they simply use in two. You just simply add some variables or take out some variables. That's all you can do. Because of that, they were suggesting some kind of another procedure in the very beginning. That means let's go to all possible regression model with the aid of certainty. How do you get the all possible regression model? It depends on how many regressive variables you have in your model. See, your model. So later on, for that particular case, when you're looking into all possible regression models, you get regression model, you get this, all the models, see? All the models, including how many you have. You have 4 variables, 4 times 4, 16, 4 squared. The first one called the empty model, and then singles, doubles. I explained yesterday how to get singles. If you have a 4, choose 1. You have a 4 of them, single ones. And double ones, you can get all the combination. Add with bonus, add with market share, add with compete, bonus with compete, bonus with market share, compete with market share. It's going to be 6. How do you get the 6? 4, choose 2. 4 combination 2. That will give you 6. And the third one is 3 at a time. Add the bonus market share, add bonus compete, blah, blah, blah. And the bonus market compete. Then you're going to have 4, choose 3. 4 choose is same as the 4, choose 1, which is 4. And the last one is out of 4, you're going to pick 4. 4 choose 4 is 1. So you have one option, one combination with the 4 variables. 4 combinations, see? 4 combination, 4 models with the 3 variables. You have a 6 models, submodels with this one. For each and every one, you were checking R squared adjusted, Mallows CP, and standard error. See? And then we were talking about the Mallows CP over here. The Mallows CP is nothing but that's the ratio between the sum of squared error to the other sum of squared error. You are just comparing the sum of squared error to sum of squared error. That means sum of squared error of this model. Let's say you are interested in this model. Sum of squared error of this model being explained by the explained by the sum of squared error of the model. Plus that they have added some terms to make this one. So for some adjustment, other than that, mainly if you focus on this one, is mainly that one. But sum of squared error of this one has been divided by mean squared error, some kind of adjustment, minus n minus 2. And if you draw this one, it looks like a curve. you can remember yesterday we were talking about that one. It looks like a curve. See, you can remember. Okay, one should be on the other one as it's this one. And also, see, CP versus P look like a curve, but if you at this place, at the very small CPs will be equals to P because they were fitting into a straight line. CP equals to P. Where CP equals to P. See, CP equals to P. What's going to happen? There. The graph. Over here. This one's CP equals to approximately P. If that's the case, you have to have the small CPs. That means small P's. That's what they say, small ones. That means that less the number, that fewer number of observation, fewer regressor line would produce like a that smaller CP. You need the smaller CP. You need the smaller one. So they say you need the smaller one. This one, chapter 3, we don't need that one. This one, chapter 3, we don't need this one. Okay. See the CSA in mode with the bias when the CP be large ones are very biased. We don't need the biased one. We need the unbiased one. Also say that the model with no bias, CP should be equal to P. When there's no bias, see, if you take some CPs from here, larger ones, the bias, see, that means they're going to be deviated. But on the other hand, you need that when they, for a smaller one, the model with no bias, if you really need the bias, should be equal to P. Bias, see, this means no bias. See? This means no bias. No bias means CP has to be equal to P. If CP equals to P, that's going to happen only for, it's going to happen if P is small, if CP is CP and if P and CP, sorry, P and CP are small, they both are small, CP to CP becomes P, CP equals to P only if you have a small CP. Small CP means small P. It is recommended that we consider model with the small CP and those with the CP near P. It's going to happen only with that smaller CP going to happen for the smaller P. So that means smaller the PCP, far better. No bias. See, no bias. You go to the smallest one. Error has to be minimized. You know, error has to be minimized. This is nothing but the standard, the spread of the error, minimized. And the R squared has to be the maximum. So you're going to pick the one with the R squared max, R squared adjusted max, CP max, CP min, this one min. That's the one. In addition to that one, there are some others. See, here that's what they say. The two variable model with the add and bonus has the smallest CP and the highest adjusted R. Not only the smallest CP, add and bonus, smallest CP, smallest SC, highest CP, highest R squared and highest R squared adjusted. The three variable models add in either market share or compact also have a small CP value, but only modest increase in R squared. They have a modest increase in R squared. See? They also that have a smallest one, but even these two, add bonus market share, add bonus compete, can be taken as the next candidates. The three of them. If you are really thinking that this is not enough to explain that the sales, you might gonna add this another market share. or for in addition to advance and bonus, you can add the market share and competition. Those will be okay too, but okay, and then see that whether it's okay by using the other methods later on. That's what we are planning to do. See, you pick this one as the best model. The out of in this all possible regression the procedure. So that one you pick this one, or you're gonna pick these two too, but this is the best. And now what they're gonna do? That see the best model, the two variable model is probably the best. That's what they say. So in that one with the large number of potential x variable, the all possible approach become unlikely. See, because the large number of like let's say that you have a variable c, the minitab, don't worry about minitab into that long mu as a few as a 15 minutes. See? But once that the computational time, that's for the minitab, but obvious this prediction can be forced in the model, that's the reason time. Not always what you want. So I mean there are limiting that because the computer get crashed, then you have a large number of regressive variable. If you go to this one and try to, let's say you have 100 variables, then you're gonna come up with the 100 square. Right? 100 square. So 10,000 models, they had to check for 10 models, they had to run the 10,000 models. It's very tedious. So this not gonna valid for like when you have a large number of, regressive variables. See? Other variables, that's why you're gonna jump into the with a large number of potential like where it may be best to use one of the iterative selection method. Those will look at only the set of models that their rules will lead them to. So they may not yield a model as good as the written by all the possible regression approach too. But through that method, see, because of that situation, with a large number of potential x variable, it may be best to use one of the iterative selection method, iterative selection method. See? One at a time. These will look at only the set of models that their rules will lead them to. See? So they may not yield a model as good as that written by the all possible regression approach. It might not gonna be that as good as the model written by the all possible regression approach, but still that's the only way you can tackle this. See, now we were thinking what would be the best the model selection procedure. Go to the all possible regression model, but we have some limitations. The limitation means that we cannot get this utilize this method when you have a large number of regressive variables. That's why we're going to jump into this iterative techniques called the backward elimination and forward. In the backward elimination, this is what we're going to do. For the variable selection techniques, we're going to jump into that one. Start with the all variables in the equation, all, whatever the variable you think of. Examine the variable in the model for significance and identify the least significance one. Remove this variable, least significance one taken out if it does not meet some minimum significance level. Run a new regression and repeat until all remaining variables are significant. So that means you're gonna fit this one. Okay. So this one, selection procedure. So this one, GM select procedure, forward selection, backward elimination, stepwise regression procedure. This is related to chapter 8. Let's say that what you have over here. See? Okay. For backward elimination by Rasi. This is a backward elimination. The backward elimination by running regression procedure. Backward elimination. I'm going to start from here, the best submodels method. See, how do you get the best submodel method? We go to our example and see. We go to sales, advertising, owner, market share, compete, selection, R squared, adjusted R squared, CP, RM squared, and the best two. If you want, you can say, give me only the two of them, only the best two out of, you saw that here, each and every submodels would have a different number. The singles have four submodels under that the same example. You saw that one. See, you can restrict that one. I don't. Sometimes you're gonna say no. I don't want to see all of these. I give me the two best one out of these four. I don't need the four of them to be seen. Give me the best two. Best two means like a one with that highest R squared and highest R squared adjusted, and the smallest CP and the SC ones. They're gonna select that one and give to us the two best ones. Even on this one, two best one. Even on this one, two best one. Here you cannot get the two, just the one by itself. Okay. So that's why I have restricted. If you want, you can restrict by giving this number and say best two. If you don't put the best two, they're gonna give all of them. Okay. And there, first I run this one. Okay, the work data file not there. Okay, that's okay. I'm gonna run this one. Once advertising. Okay, let's go to this one. See, I'm gonna run with the all of them. See, the all possible regression, but it will display all the submodels. See, one have 4 of them. With the 2 variables, you have 6 of them. With the 3 variables, you have 4 of them. For the 4 variables, you have 1. I'm gonna say no, I don't want to see all of these. That the same way that I have seen on the that my PowerPoints slides. Okay, I would say that give me just a best two from each and every category. They have reduced this. See, singles one you have 2, the double ones you have a 2, triples one you have a 2, and the 4 variable you have 1. See, these are the best one. This is enough for you to have a look at it and see, pick the best one out of it. I'm going to go ahead and look at the best one by looking at this.
Okay, so sorry, I just want to, can I repeat this back to you to make sure I'm understanding it correctly?
One with this one with 1. Let's see what's going to happen.
Do you hear me?
Now what?
Hey, do you hear me?
When you have a 180, 5.101, 81. When you have 285, 84, 1.6, 90. Hello, yeah, okay, go ahead.
Hey, hi.
Go
I
ahead,
just want to
Angela.
repeat it back to you to make sure that I'm understanding it correctly. So by using this, sorry, oh, no, that's my block. By using this like selection R squared adjusted best one, what we're saying is compute the model, and then at every like factorial or whatever, like at every level for every number of variables in n number of variables, give me the best model based on those 2, or maybe it's 3 right here, but these previously outlined like R squared, R adjusted CP, R MSE, by using those metrics.
Yeah, exactly, because we were reducing that one, and out of this, all these for each submodel, the way that I pick over here, when I put one for each submodels with the 1 variable or 2 variables or 3 variables or 4 variables, these
okay.
Are the but
so if we put enough. 4 that's right here, if we put best 4 right here, we would get 4 number ones, and it'd be each one of these, right?
Yep.
Each but one. Okay.
What we're looking for. Yeah. Even out of this one, because I'm not interested in throwing all the variables into that one. I really need to get into the one with the best model. Best model would have the highest R squared adjusted R squared and CP least 1 and the root mean squared least 1. So I don't care how many variables there. I was really interested in the one that these quantities
that explains the most variation overall.
Yeah. Overall, because in the beginning when I run in this one, look at when I was running this one, it was showing pretty much all possible regression model. I'm not going to use all these regression model. There's no such thing. No, and we know for sure. But then now we have an issue ahead of us that, okay, which model am I going to go ahead and pick? In order to pick that one, we have a criterion. What's the criterion says? Criterion says pick the one with the highest R squared, highest adjusted R squared, and the least CP and the least root mean squared. So if you cannot.
Okay, so this is just a filtering. This is just a filtering mechanism.
This is a filtration. This is a filtration. This is a filtration of the model. I mean, this is the whole thing. The model being and this is one of the possible best selection model means we're going to filter. But when you filter, instead of looking at the 16 of them, let's say 15 of them, it's easy if you're going to narrow down this one to the best one. That best one doesn't mean you're not going to keep all of these. No, no, no. Again, this is for only my convenience to get the best one. I'm going to call that one best one. Now you have a best one from the one singles, best one from the doubles, best one from the triples, best one from the four variables. Out of this one, now again, go ahead and see which one would have the highest R squared, highest R adjusted, least CP, and least root mean square. You can clear cut see that this will give you that number. See, that's the one you're going to take out and say, hey, I'm not going to throw that market share competition to explain this one, and then it's a waste in my time, labor, and then it costs a lot because if you throw variable that we don't want to, then it's a lot of time consuming. So because of that reason, we pick the best one. And then now we have a question ahead of us. Would that be the best again? See, would that be the best? Because that we have to get this verified. That's why we're going to jump into that backward and forward selection, backward elimination, forward selection, and stepwise selection procedures. And then again, can we get the best model out of that one and see whether we're going to come up with the same thing. Because as of now, we're going to stick to this one. My best model would be advertising and bonus would be more than enough to explain the wages. The other market share or that competition would not that much important in explaining that one. See? So it's a filtration. We filtered that submodels. Now we filtered the variables. Two things you are doing. You are doing data mining. Data mining means your unnecessary variables are taken out. Variables are taken out. Plus unnecessary models are taken out. Two things, two processes are done by this all possible model selection procedure. So now we're going to jump into this one. In the backward elimination, it says clearly, backward elimination says this one here. See, backward elimination says start with all variables in the equation. Examine the variable in the model for significance and identify the least significance one. Remove the variable if it does not meet the some minimum significance level. Run a new regression and repeat until all remaining variables are significant. We know that one. So what I'm going to do, I'm going to throw all the four variables in this procedure, backward elimination, and run. I'm going to run this one. But at the end of the day, I don't even have to do this so many times. It's been done by the one line. Okay, but let's go over here. Look at this one. This one, 0.03, less than 0.05. This is extremely small. See, this one, less than 0.05. These two are not significant. So out of these two, now again, they say to which one to be taken out. You have to take out, not the both. One at a time. One at a time. Which one you're going to take out? One with the, see, remove the variable if this one means the minimum significance level. May identify the least signal. Run a regression.
I would say it's the compete one, right? Because it's the highest value.
Highest value. That highest value will not even get closer to that one. No, it is, so you're going to take the compete. So that's the same thing they were explaining our, oh, sorry. Here they say that backward limitation, backward. Remove the variable, it does not mean that identify the least significant one. See, that's the least significant one. That's the key. So we already identify which one is the least significant. There are two significant, minimum significance. See, some minimum significance or least significant one. So I'm going to take out compete and then do the same thing again. Now I take out the competition and I'm going to run again. Let's see what's going to happen. See? When you run that one, see, this one significant, the B not, do not worry about the significant. This is the least significant or the only significant one. I'm going to take that out, remove. Elimination. You're going to eliminate. It's like, see, filtering. Now I'm going to go ahead and run these two. Okay. With the advertising and bonus. That's the same model I got with the using the different procedure called the all possible model selection procedure. Let's see, it's going to be consistent with that one. See, now what? Both are significant. There's nothing for us to be removed. So we're going to stop here. When it comes to the point that all are significant, we stop here. See, that's the same thing we got from the other procedure as well. Can you remember? By running this method, I'm sorry, this method, see, this method too, see, through this method, we got this on all possible, or the base model procedure, we got the same thing, advertising and bonuses are more than enough for you to explain that one, see. Now we're gonna go ahead and do the other way around. Now let's go to the forward selection. Forward selection, they're gonna say, at each state, it looks at the x variable, see, not in the current equation, and test to see if they will be significant if they are added. You're gonna see when they were not in the model, but your current equation, but you're gonna test and see whether this would play a heavy role in explaining that y variable. If they see that one will be checked in this first stage, the x with the highest correlation with y is added. In the first stage, the x with the highest correlation with y is added. At later stages, it's much harder to see how the new x is selected. Okay, let's see that. See, correlation, in order to do this one, I'm going to go ahead and looking into the correlation. Which one has the highest correlation with x, okay? Or y. Highest correlation with y variable. Here, y variable is nothing but the sales. Let's say out of these four variables, which one's going to show that highest correlation with sales? That's the one I'm thinking about adding in the very beginning. I'm going to go ahead and look at the sales. See, sales, advertising, 0.9, bonus 0.5. See, this is the highest one. So this is the one I'm going to add to the model in the very beginning. See, advertising. See, I'm going to run that one with only with advertising. And advertising, you add the only thing, only that the advantage of this method is, and you can check and see whether this is going to be important or not. See, significant. You're going to keep as it is. If it is significant, you keep it. Advertising. Then what? Then go ahead and look at which one. Then go ahead and look at what is the next highly correlated one with this guy. Let's see that this one more time. Who is the next highly correlated one? See, bonus. Even these two are not even played that much of it. 6.5. I'm going to add now bonus. See? Advertising bonus. See? And see whether the newly added one will be important or not. Anything is important. See? Important. I'm going to keep as it is. Then let's go to the next one. Next one would be the market share. You can remember market share of which one is the next one? Sorry, I'm going to run this one more time. Correlation. It says which one would have no compete. It should be the competition. Let's add the competition. I'm going to do the other way around. Competition. Not significant. Take it out. Take out. If not significant, I'm going to take out. That's why they say in this first stage, at later stage it might be hard to see, but you're going to see it will be significant. If they're significant, that will be added. If not significant, they will be taken out, not added. We're not going to add. That's why we have to say not removing. I'm not removing. I'm just on the threshold of adding. Before I'm going to add that one, I did the test. We failed the test. So you're not going to add. We are not telling that we are removing. We say we do not add. We're not going to add that one. Okay. Then we're going to add the next one. Next one is the market share. MKTSHR. Market share. And add the market share. Now, we trying to add. We haven't added yet. We are trying to add, but before that, we're going to add that one. See, 0.4. Insignificant. We're not going to add. We're not going to add. Then we are left over with the two that we had. See, even through this one, we came up with the best model via forward selection. See, only sales and advertising. If you want, you can run one more time. And see, are they important again? Yes. So, see, now it's been convinced, even through this forward selection procedure, that the way that excuse me, that whatever that what we got the model, the best model through the all possible selection model procedure is same as this one that came through this forward selection procedure. Now we have a third method. Look at the third method. Let's see this one. Stepwise selection by running regression procedure with one variable. Step 1, fit each of the one predictor models, each one, that is regress y on x1, regress y on x2, regress y on xk. Of those prediction whose t-test or p-value less than alpha 0.0, and thus predictor put in the stepwise model is the predictor that has the smallest t-test and p-value. If no predictor has a t-test or p-value less than alpha pointer, stop. That means you're gonna check all of them, not one at a time, not the way that I did over here, not only advertising. I'm gonna check the sales versus advertising, sales versus the bonus separately, sales versus the bonus, sales versus the competition, sales versus market share. That's what we're gonna do in the stepwise one. Okay, later on we can come to the steps. See, advertising, bonus, market share. See, we're going to run separately and see whether any of these are the first predictor put in the stepwise model is the predictor. See, to those two predictions, anybody's p-value will less than alpha or extremely small, the first predictor put in the stepwise model would be the predictor that has the smallest t-test or p-value. See, I'm going to run all of these. I'm going to run all of these separately. Run and see which one has the most significant one. See? Okay, let's see the most significant one. That means this one, advertising. Okay. See here, p-value. This one, that for the bonus, p-value. This is that one. P-value. The market share, this one. Sorry, competition, this one. In competition, you have 0.06, 0.06. This one, 0.9 market share. This one, bonus, we have a 0.030. And for the advertising, we have a extremely small one. So you're going to pick the one with the smallest one. That's what they say. Step, sorry. Here. Okay. Of these predictors, get the smallest p-value. One with the smallest p-value will be added. That means I'm going to add to the one out of those, all these four. I'm going to add the advertising to that one, right? That one. Then which one you're going to add at the next step? That's why we were talking about here. Okay, done. Step 2. Suppose that x1 had the smallest t-test p-value below alpha blah 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 there, and then we can deem to be the best single predictor rising from the first step. Now fit each of the two predictor models that include x1 as a predictor. That means now you're going to regress y on x1 and x2, regress y on x1 and x3, and regress y on x1 and xk. That means keeping that x1 with in the model, which is advertising in the model. The rest will be two at a time, will be run with this one, and then see which one has the smallest p-value. See, I run like that one, and let's say this one. And if no predictor has a t-test p less than alpha, stop. The model with the one predictor obtained from the first step is your final model. But suppose instead of that, x2 was deemed to be the best second predictor, and it is therefore entered into the step 5 model. Now, since x1 was the first predictor in the model, step back to see if the entering x2 into the step 5 model somehow affect the significance of the predictor again. See, this is what we're gonna do. We ran this one, two at a time. Okay, we ran two at a time. And the two at a time, and then see the p-values. No, not this one. I think that's not it. No, not this one. Sorry, not this one. We are here. That advertising and two at a time. Sorry, this one. Two. Yep, right. See, bonus, bonus and advertising 0.01. Advertising and this one 0.6 market share. 7 something. Around that one stay over there for sure. Okay. Why we have a 3 of them? Oh, sorry. It should be here. These four. 1, 2, advertising bonus, advertising market share, 3 of them, advertising competition only. So we're gonna try to add 2. Bonus 0.01, 0.6, 0.7. Okay. So out of these 3, we're gonna keep the one with the least p value. See, this p value. So I'm gonna keep the one with this one bonus. See, bonus. See? And not only that, once you keep that one, they say once you keep that one, okay, say now since x1, they say that okay, if no predictor, say they say by suppose x1 has the smallest t-test and in the like the advertising. Now you're gonna run that one with the other predictors, advertising and bonus, advertising and market share, advertising and the competition. Then of this prediction, whose TP is less than this one, the second predictor put in the set 5 model is the predictor that was the which has the smallest p value, which we found the second one would be the bonus, which has the smallest p value. If no predictor has the t-test less than this one, you stop. We know that. But suppose that instead that x2 was deemed the best one. X2 means like in this case, the bonus. Second predictor, and it is therefore entered into the model. Now entered in the model. Now since x1 was the first predictor in the model, step back and see if the entering x2 into the stepwise models somehow affect the significance of the predict. That is, check the t-test p-value for testing beta 1 is the t-test p-value for the beta 1 has the become not significant. That is, the p-value is greater than alpha or remove x1 from the stepwise. Now, what are you going to do? Now you're going to go ahead and check again about the first one. And now 2 of them are in the model. Now you're going to go ahead and check the first one. See, since the x1 was the first predictor in the model, step back and see if entering x2 into the stepwise model somehow affected the significance of the predictor. That predictor, okay, that particular predictor x1. That is, check the t-test p-value for testing beta 1 equals 0. If the t-test p-value for testing beta 1 equals 0 has become not significant, that is, the p-value is greater than alpha, remove x1 from the stepwise. See, that means they were telling this one, you have to go ahead and check x1 now again. Okay, I'm gonna go to this one. It's already run advertising and the market share. With both of them, if you want, you can run again. Okay, here I'm gonna come back before go to advertising bonus, advertising market share. Again, you're gonna write this one by itself because I thought that this one, the bonus has the least p value. Okay, I'm gonna run this one again. That's what they say. Run this one. And see whether x1 is important now. Now we are trying to, after entering x2, x1 being covered by that one. See, I'm gonna check this one now again. Now we check again. See, significant. Then you keep as it is. If it's significant, you keep it. If it's not significant, you take out. That's called a stepwise. You added in the beginning, but again it will be checked. That's the best thing about this setup. Whatever you been added, if it is not playing any heavy role, you can remove that one halfway through. Or if something is not being removed in the beginning, they can be added again. Can you remember? in the beginning, see, if something has been removed, see, in the beginning, see, bonus, market share, competition, out of that one, you remove the bonus. Later on, you get a chance to add the bonus. See, you get a chance to add bonus. And again, even though that bonus been added, you're going to check and see now advertising is important in explaining. Once we come into the picture, whether this guy being overshadowed by this guy, you check that one. That is good. Now you go to the third model. The third model you're going to do with those two in the already in the model, you're going to add the third one. Third one. Now, if you have a fourth one, you're going to add. Now you're going to add the third one. 3 at a time. See? 3 of them. Since we have left over with only market share and the competition. See this one. I'm sorry, this one, and there should be another one too. Bonus, market share, P value and others. See, P value variable and others. So we are missing one here. Oh, that's the one. So these two, these two, these two, these two. Those two already in the system, and I'm going to check the third one. Can the third one be added to this one? We have 3 of them. Then let's check the P value. If market share, the P value of this one is 0.47. This one is 0.5. See, competition. So which one we're going to take out? One with the market share, highest P value, see, highest, least significant, highest significant, insignificant one. This one competition is 0.5, it's very higher than market share. Sorry, market share is 0.4. So gonna take that out. See? So they both are not significant. See? Actually, at this stage, smallest P values, if they one, see, they were not significant. If they were significant, least significant one will be taken out, but unfortunately, they were insignificant. That's why they say at the third step, see, second step. We are still on the second step. Second step, this one, see. Suppose this one has a, see, step 2, step 1, step 3, no, this is step 3. Step 3, this one, that is P value is greater than this one. We did this one, this single model is X1, we check that one. Suppose X1 and X2, which are mean like a, now we know that in the third step that we did. Okay, bonus and advertising and bonus into the 2 predictor step by model and remaining term. Now fit each of the 3 predictor models that include, and that means we're going to do advertising bonus with the market share. Okay. Advertising and bonus with the competition. And then of those predictors whose test P value less than alpha, the third predictor put in the stepwise model is the predictor that has the smallest P value. But if no predictor has the P value less than alpha, stop. The model containing the 2 predictors obtained from the second step in your final model. Yeah, that's what happened here. They both would have insignificance, larger P value, so larger than 0.05, they stop over there. That's what they say, stop there. So under that one, we're gonna have only, I don't know that. Why we type in this one again here? Suppose step 2. Okay, step 2. Then if you want to type in here that this one, this is the place we have to type in. Okay. And to type in like this. Why there is this step 2? This is step 2. But step 1. I'm gonna go like this. Okay, I do like this. It's easy. Okay, I'm gonna get this one. Step 2 whole thing. Cut. and paste after step 1. See, step 2, step 2, paste here, step 1, step 2, this one, and this one. That's step 2. I'm gonna keep like that, and then I'm gonna take this out. I don't need this one. It's redundant. That's step 2. After step 2, okay. When we go to the steps 3, I'm gonna cut them out. Step 3. Cut. So step 1. Oh, step 2. Step 3. With the 3 of them. And this one. And I think to here. Then can see like that. And this one via step by selection with the this one. See, 2 of 1 would be the same. See, we came to that one. Now, instead of going in this rigorous procedure, it's very easy. One shot you can get this done by this function. You go to GLM select, see, forward selection, backward elimination, or stepwise selection procedure can be easily obtained by go to data, and model would be sales, advertise, put everything. They will decide. This is the thing. This is called significance level to stay 0.05 or entry. Entry means if you are trying to enter, can you remember we take out? We didn't allow them to enter. This is the level of significance for that one. This is the level of significance for that one to already in the system to stay. If you really want to stay in that one, that would be, you would pass, the p-value has to pass 0.05, less than 0.05, significant. Here, somebody try to get into that one, it has to, its p-value should be less than 0.05. That's what they call the cell stay and a cell entry. Significance level for stay, significance level for entry. You can write one at a time. Let's say I'm going to write the selection stepwise. Okay. One shot. You don't need to go through that rigorous procedure, shortcut. Okay. To get the advertising and bonus. That they have already done. We don't have to worry about that one. It's already there. And let's go ahead and run. I'm going to get rid of this one and then run forward selection. Okay, I can get rid of this one. Okay. Sorry, backward selection. That's a stepwise one. Let's go to backward selection. You can remember how the backward selection. Again, okay, backward selection. What do you have? I'm sorry, here, advertising and bonus. See, that's the last one. Same thing. Let's say that you are, instead of that one, you are planning to use the forward selection. I'm gonna get this one. Forward selection. Forward selection. Again, advertising and bonus. Everything is convinced. So when you have to do, if you want, you can do like this rigorously. You don't have to. No, this is for your own practice. You can remember how we did the different things. Forward selection, backward elimination. In the backward elimination, all and take out one at a time, and then come up with the best one. Forward one at a time. You adding one at a time. Forward, you're adding one at a time. Which one you're going to add in the very beginning? One with the highest correlation with one, and keep going until you're done. And stepwise one, you're going to add the one, all one, doesn't matter highly correlated or not. Singles one, check out of that one with the least highest significant one, you're going to keep highest significant, and then you're going to do 2 at a time. And you're going to keep the highest significance one. And then you're going to keep 3 at a time. Okay, highest significance. Those are 3 procedures. So those 3 procedures you can easily add to your homework over here. So that's what we were doing here. See, you have a slit data. I'm running that one. You see, and even the all possible method procedure too. See. So let's say that you are using all possible regression model for the wages one and log wages one, forward selection, backward selection for the log one wages. And this is for the fish one, fish data. You don't have to do both of them in one of them. Okay. So let's see what I have done here. Okay, this one up to there. Okay, good, good. All possible models. Okay, let's try to get the all possible models. This is very hard to looking into this one. Let's go ahead and narrow this down and say, hey, I really need one with the, can you remember that, to go over here, this one, and keep the best one. Best one or two, you can see, best one. And I would say, give me the best one. Best with only single, best equals one of the model now from the whole combination. Now for the single one, the best one, double one, best one, triple one, best one, 4, best one. So out of this one, which one would be the best one? One with the highest R squared, highest R squared, highest adjusted R squared, least CP, least RMS, root mean squared error. Looks like 0.29, 29, 3, 6.59, like this one. No? Education, age and gender. Education, age and gender. Let's see that whether we're going to get the same thing out of this method, one of these methods. Okay. Yes, education, age and gender. The other one has been taken out. See, that's the best one. Education, age and gender. Let's see that whether we're going to get that one from the other procedures as the forward selection procedure. So this one. So let's run this one and say with the forward one. Same thing. And stepwise. Let's say with the stepwise, we're going to get the same. GLM select function. Education engine, same thing. And through this one, we get the same thing. And then we're going to do this one for the log one too. If you want, you can do the same thing for the log one. And you can talk about the best equals 1. Let's see the highest one, 0.3095. So also 3095. 3089, this one 88 is the least one. is the least one, 41. Okay, again, 3 of them. We can check even the log wages, whether we're gonna come up with the same procedure. I'm gonna just run one of them. Okay. Just give you the 3 of them. See, they selected already. So this, what is this one there? We can try this one with the other way around by using the dummy variable. I was trying that way too. All possible one, I'm gonna say give me best one, best equals 1. See, this one also with the same thing with the log, best equals 1. See, if you run those two together, let's see what you're gonna get. Let's see. So 97, the least, highest. See, education, age, and gender. Gender is represented by women. See, so not the language. Language you don't need. See, so again that one, and then same way. Then for the log one, that's for the log one. For the other one, where's the log one? See here, sorry, log one. See again, least 4184. So 4185, 2.3, 30, 89, 3095. See again. Education, age, and women means dummy variable has been utilized to indicate the gender. See, either that way too. See, again come. See, the same thing we're gonna check with the aid of that other procedure too. With that is for the all possible one. This one, the forward selection and backward selection method would produce the same thing or not. See, when we have a dummy variable. With dummy variables, without dummy variables. With dummy variables. See, what are you gonna have? See, education, age, and women. See, that means this one for the log one. The other one, education, it's the same. Very interesting. I mean, like that's the beauty of this programming and everything, that if you're gonna couple that, not the theory, I mean, like at least that the process behind that one, that's gonna be very useful. See? So this is how we have to answer and then come up with the best one. They were telling me we have to do the same thing, but they don't specifically say that for the second one, instead of weight, what are you going to put over here? So you can arbitrarily put one of them. Okay, I'm not going to go through that one in detail, but length one, see, or whatever. If you want, you can put the height. Doesn't matter. See, they don't say clearly what you're supposed to put. They do the same thing by the group by species. Then the same thing. Yeah, weight by height. Group by species. This one, scatter plot of weight. With 10. By species. Let's see a little bit, and then we can stop the rest. We can cover next time. See, the scatter plots and their lines. Different species. So you don't have to do both of them, one of them. Then again, that this has been done. It's the same thing. So SG plot, data sleep run. That's a number 2 scatter plot for the all of them scatter plot matrix. It's a scatter plot matrix. And the second one, we say that to create a two group scatter plot for the wage and education, same way the wage and education. I was taking weight and height, see weight and height, and by species. One says label variable and the other one using the language. So we have only one only one categorical variable. So you have to do this by only by species only. I don't think that we need the second one. We cannot. And the third one, create a regression model using the wages as dependent variable, education and age as independent variable. That means seems like that. See, when you have that this one, you can run that weight, the regression, see the model with the same way that we did for here. This one, number 2. All this for number 5. See, number 5 for all the possible, see, all the way up to here, number 5. The first data set. For the second one, second data set, the number 2 is this one. We don't gonna do by the language because we don't have another categorical variable. So you can use this one. See, wages, see, education and wage, education and wage. See. To do the education with the education, the other one wages, create a regression model using the create a two group plot and one section label. The number 3, create a regression model wages as a dependent variable and education and age as independent variables. You don't need this one. This one. Both are together. See that one. You want to go together. So pretty much similar fashion that you can run. They were adding both regressive variable, both quantitative variables. If you want, you can do the same thing over here. I don't need this one. This one, paste. I don't need this one too. You can say this one is the fish data. You can add pretty much the weight. You can say the length one, length. One, length 2, length 3, and height 10. Let's see here. Height 10, weight, width. All the quantitative variables. I'm going to take this out for time being. And that one too. So you can get all the discuss about that one by looking at this on which variable can be kept over there. So are they all the variables are important in explaining? Looks like, see, you can see clearly. Most of the variable height, okay. The rest not gonna that much important, okay. And then overall test and all kind of thing you can discuss. And that one in number 4, they were telling that the log one instead of that one, you can put the log. And the same thing, no, instead of this one, and then 4 paste. Make it number 4. Instead of this one, you can do the log. But the thing is that we don't have a log. Okay, we have to create log. The weight has not been, but in the previous data set, log has been taken. That's why they say that log has not been taken. It's a little bit work for you to take the log. That's the same thing that we saw in chapter 5. Can I remember here? When we were talking about the logs, different types of log regression. See, but that regression log has been given. Okay, that's chapter 5. But when it comes to homework 2, the logs being taken in that data, the GDP. So no, sorry, this one they haven't given. See, you can create that logs. See, create the logs and then put it back. See, log rec, data set names, log rec, whatever the data set, as a similar fashion that one. So you have to create logs. So you're gonna go to that your data set, data out.fish, and then you can use the same thing here. Data out.fish. Call that one log weight, WEIGHT, and which means you are taking log on weight, WEIGHT. And you don't need this one, imports. That's the one you're gonna utilize here. Call that one log G. You have the same thing now still. Okay, this one. Weights, new one, and that will be utilized in order to explain this regression. Reg or GLM doesn't matter. Like that. And number 5 would be that pretty much the same thing that we did. See, started from here. See, you have to do on the whole thing. Now, see, you can run any way that you want because of that. See, if that species has been given with this name, you have to make sure that if you are planning to include that one too. Sorry, that we have to check something here. I think I didn't check something here. That one section language in uploading this one and the goes with the model. Select the grouping variable that creates the select the grouping variable that creates the best model. Use grouping variable for section language and add those to the model. See, those are the add to the model and get the that one. Now they're gonna tell that one in the 5th one. That's what we did like that. In the 5th one, sorry, number 5 here. That's why we did this modification. See, we did this modification. We didn't change. You see, this one you change to that one to see numbers. If you are planning to that run that language reg, see regression. When we were running that one, let me see that in a similar way. If you want to do similar way, number one, scatter plot. Second one, number 2 here. Let me see number 2 here. I will see. Okay. Okay, this one good. Matrix good. All the variables you check. All the scatter plots come only for the that quantitative variables. We did this one. We did the scatter plot separately rather than matrix. And third one, we have this one. We have this one. Fourth one. That's it. No? So later on the 5th one is the one that we get started that including this guy, these two, both of them. Okay, that's right. So when you're gonna add that one, you can get this one done the same way like we did over here. So here number 5, this one, we get this one copy. And we don't have another variable like this. Okay. This is the extra way of doing that one too. But here definitely, if you see the names should be given numbers. That's what we are trying to say here. Okay. So go to this one. Okay. Their name should be taken out. The number 5. See? So you go to fish data, fish, and put it back into same thing, fish. Okay, now we're gonna say we have a, not the gender, we have a name for species. I think that name for, go to data set, let me see. No, not that one. I would like to go to this data set for the homework number 3 assignment. Homework 3, fish data. Let's see the fish. Yeah, that's the amount of the species. So we have a, can say, those are the species. Species. We don't need this one. If species equals those names, see, real, see, you can say, see, you can give a number, see, you can say that then species the 0, like that. Okay, I think we would better to use this set because it has more. Species first. Real. You can say then species 0. So same way, and what's the next one? Okay, gonna take this out and then we have the other kind. Let's see, the other kind. And Roj, and you can say 1. You can say control and species. And whitefish. And say 2. Say 2, 3. Bird. What's the other one? Pipe. Oh. Then the other one smelt. This one, and then not this one. That's a different way of doing that one. Now you can see. Now now you can run with the aid of that one, to including that guy too. So we don't need the title. So we have this one. Sorry, weight length. I'm sorry, this one. Weight length from this one. All of these plus. That's the one that we have to make sure. See, they have added all all quantitative variables, 1, 2, 3, height, width, plus our new one, species. That's the categorical one with the dummy variables, not the dummy variables, with the numbers. Okay, you can run that all the way up to here. So length 1 not found, length 2, length 3. What do you mean by it? Variable length 1. Oh, length 1 not found. Oh, maybe spellings over here. Length 1, length 2, length 3. Height, weight. What did they say? Not found. No, they didn't do anything. Species. Plus this one, see, this is the one new one. We have changed that one to that gender. See, can you remember we changed this one to gender, the primary stage. You have a gender. You have a language reg. Where's the language reg come from? Call that one language reg. We call the new one language reg. Okay. That's the, yeah, that's the problem. We have to give a new name. Okay, we have to give a new name. So we call this one sex become gender. That's why I'm going to give a new name. But I gave the same name, that should work too. Species. Spec. Okay, let's say spec. Spec equals 0. 0. 0. New name. Species. Here, this one. Sometimes that being height. Height is the problem. Smelt. Okay, pipe. Search like okay. Let's try this one. Okay, we are rather. Huh? That fish. Yeah, you can check that one. I think that okay. The same way we did over here, the same thing. I'm doing the same thing because I'm giving a new name. But they came with this names, categories. There are 3 English, French like that. We're gonna change that one as 0, 1, 2. So this one 0, 1, male, female. 0, 1, 2. Language, French, others. See, that's the same thing we were doing here. 0, 1, 2. I think this spelling somewhere mistake. I think you can check that one anyhow, and then you run again with the. Oh, sorry, we didn't even use this one. Okay. Okay. See one more thing. Let me see what they have. What the error message says. Onion or nodes to log. They don't say anything. So if that's the case, the best thing that you can get this done using that dummy variables. See, like this dummy variable, you can set up like that one and get this done. It should work, but there's sometimes somewhere that some names are missing or something like that. But that's okay. That you can have a look at it. I'm gonna have a look at it too. That so you have to do one of these. It's not a big deal. Okay, then this one you can have a look at it. I think I have to clearly see that the names. I don't see clearly. Brian, you can stop over here. See. Okay. What I'm gonna stop over here, have a look at it, this one, and give the numerical values, and then get this done. Or that go to the dummy variables and get this done, and then do the same thing. But you don't have to do both of them, just one of them. It's easy. Up to here, you can. If you selected that the other data set, this data set, split data set, then that's it. Yeah, we can continue this the rest next Monday. Do you have any question? If not, I'm planning to stop over here, and then you have a good night, and then nice weekend.
Yes, I don't have any questions. Thank you.
Take care. Okay. Thank you very much.
Okay, bye.
Thank you. Okay. See you on Monday. Take care. Bye-bye. Good night.